The year was 2013. MOL Comfort, a massive container ship, was sailing through the Indian Ocean. Suddenly, without warning, the unimaginable happened. The ship, in calm seas, cracked. The two halves drifted away, taking 4,293 containers with them to the bottom. The event sent shockwaves through the maritime industry. How could a modern ship, seemingly in its prime, simply break in two? This catastrophic failure served as a stark reminder of the immense forces at play on the open ocean. It underscored the critical importance of understanding the complex interplay between a ship's design, cargo, and the unforgiving environment it traverses. The MOL Comfort incident became a tragic case study, prompting investigations and raising questions about the safety and resilience of modern maritime vessels. While the image of a ship snapping in half might seem like a scene from a disaster film, it highlights a critical aspect of maritime engineering that often goes unnoticed by the general public. Behind the scenes of every successful voyage is a carefully calculated balance of physics, engineering, and design. Understanding why ships break requires delving into the fundamental principles that govern their structural integrity. This essay aims to shed light on the hidden forces that ships contend with, the science behind their construction, and the lessons learned from maritime disasters like that of the MOL Comfort. By understanding these factors, we can better appreciate the challenges of maritime engineering and work towards preventing similar tragedies in the future. Before we dive into the mechanics of ship failures, it's helpful to understand the basic anatomy of a ship's structure. Think of a ship's hull as a giant hollow beam. This beam is subjected to bending forces, much like a ruler held at both ends and bent downwards. The top of the hull, similar to the ruler's top, experiences compression, while the bottom undergoes tension. The strength of this beam, or hull, depends on several factors: its shape, size, and the materials used in its construction. A crucial element in this design is the backbone of the ship, known as the keel, which runs along the bottom and provides longitudinal strength. Attached to the keel are ribs or frames which provide transverse strength, much like the ribs in a human body. Over these ribs, the ship's plating, the skin of the vessel, is attached. The plating, typically made of steel, forms a watertight barrier and contributes significantly to the hull's overall strength. The thickness of the plating varies depending on the ship's size and the expected stresses it will encounter. Larger ships require thicker plating to withstand greater forces. Understanding this basic structural framework is key to comprehending how ships behave under stress. The balance between the forces acting on the hull and the strength of its components determines whether a ship can withstand the rigors of the open ocean or succumb to the immense pressures of the sea. In the following sections, we will explore these forces in greater detail. Ships, despite their impressive size, are at the mercy of the relentless forces of nature. Waves, wind, and currents constantly act upon a vessel, creating a complex interplay of stresses and strains. One of the most significant forces is wave action, which can exert enormous pressure on a hull. Imagine a ship sailing head-on into a large wave. The bow or front of the ship rises with the wave, while the middle section experiences a downward force. This creates what is known as a hogging condition, where the ship bends upwards in the middle. Conversely, when a wave passes beneath the middle of the ship, it lifts the hull, causing the ends to sag downwards. This is referred to as sagging. In addition to waves, wind also exerts significant force on a ship, particularly on its superstructure and sail plan if present. Strong winds can push a ship sideways, creating a sideways force known as leeway. This sideways force can be particularly dangerous if it acts in conjunction with other forces, such as waves striking the ship from the side. These external forces are compounded by the ship's own weight and the distribution of that weight. An unevenly loaded ship, for example, with most of the cargo concentrated in one area, can create dangerous stress points, making it more susceptible to structural failure. Understanding these external forces and how they interact with a ship's structure is crucial in preventing maritime disasters. The forces described in the previous section subject a ship's structure to various types of stress. Two important ones are beam stress and bending moments. Beam stress refers to the tensile and compressive forces acting on the hull as it bends. As mentioned earlier, the upper portion of the hull experiences compression, while the lower part undergoes tension. Bending moments, on the other hand, relate to the force that causes bending. Imagine a ruler again. The further you bend it, the greater the bending moment at its center. Similarly, a ship experiencing significant hogging or sagging will encounter high bending moments. These moments are highest at the deck and keel, where the structure is furthest from the neutral axis. Another important concept is stress concentration. Think about a piece of paper with a hole in it. If you pull on the paper, the tear will likely start at the hole. This is because stress concentrates around discontinuities. Similarly, on a ship, any opening, hatch, or structural discontinuity can become a point of stress concentration, making it a potential weak link. Ship designers use sophisticated computer models and extensive testing to analyze these stresses and ensure the vessel can withstand them. However, unexpected factors like corrosion, fatigue, or extreme weather conditions can compromise even the most robust designs, leading to dangerous situations. Section 5. When ships break, the MOL Comfort. The tragic case of the MOL Comfort vividly illustrates what happens when these stresses overwhelm a ship's structural integrity. While the exact cause of the incident is still debated, investigations highlighted several contributing factors. One theory suggests that the ship encountered a series of large waves that caused excessive hogging and sagging. Another theory points to the possibility of uneven cargo loading, which could have created localized stress points, weakening the hull. It's also possible that a combination of factors, including material fatigue and undetected structural issues, contributed to the catastrophic failure. The MOL Comfort, like all ships, had a bending moment limit, a point beyond which the hull could fracture. When this limit was exceeded, likely due to a combination of the factors mentioned above, the hull cracked, leading to the ship breaking in two. The incident highlighted the importance of accurate cargo loading, regular hull inspections, and the need for robust designs that can better withstand extreme conditions. The maritime industry learned valuable, albeit tragic, lessons from the MOL Comfort disaster. Following the incident, new regulations and guidelines were implemented to enhance ship safety and prevent similar incidents. These included stricter requirements for hull strength, improved cargo loading practices, and the development of more sophisticated weather routing systems to help ships avoid hazardous conditions. While understanding the forces acting on a ship's structure is crucial, equally important is the role of buoyancy and stability in preventing ships from breaking apart. Buoyancy is the upward force exerted by water that opposes the weight of a floating object. For a ship to stay afloat, the buoyant force must be equal to or greater than the ship's weight. Stability, on the other hand, refers to a ship's ability to return to its upright position after being tilted by external forces like waves or wind. A stable ship will resist capsizing and right itself, while an unstable one may continue to tilt, potentially leading to a capsize. The shape and distribution of a ship's hull play a crucial role in determining its stability. Ships are designed with a center of gravity and a center of buoyancy. The center of gravity is the point where the ship's weight is concentrated, while the center of buoyancy is the center of the volume of water displaced by the hull. For a ship to be stable, the center of gravity must be below the center of buoyancy. When a ship tilts, the center of buoyancy shifts, creating a righting moment that helps return the ship to its upright position. Understanding these principles is essential in designing ships that can withstand the dynamic forces of the ocean and maintain stability, preventing catastrophic events like capsizing or breaking apart. The choice of materials is as crucial as the design itself when it comes to building ships that can endure the harsh marine environment. Steel, with its high tensile strength and affordability, has been the mainstay for ship hulls for over a century. However, even steel has its limitations, particularly when exposed to the corrosive effects of salt water. Corrosion weakens steel, reducing its load-bearing capacity and making it more susceptible to cracking under stress. To combat this, shipbuilders use various methods like protective coatings, cathodic protection systems, and regular maintenance to minimize corrosion and prolong the lifespan of a ship's hull. In recent years, alternative materials like aluminum and composite materials have gained traction in shipbuilding. Aluminum, though less strong than steel, offers excellent corrosion resistance and is significantly lighter, making it suitable for smaller vessels and superstructures. Composite materials, on the other hand, offer an even higher strength-to-weight ratio and exceptional corrosion resistance. However, their high cost and complex manufacturing processes currently limit their widespread adoption in large-scale shipbuilding. The ongoing research and development in materials science hold the potential to revolutionize ship construction. Stronger, lighter, and more corrosion-resistant materials could lead to ships that are safer, more fuel-efficient, and have longer lifespans, pushing the boundaries of maritime engineering. The maritime industry has learned valuable, often tragic lessons from disasters like the MOL Comfort. These incidents have led to significant improvements in ship design, construction, and operation, making the industry safer than ever before. One of the key takeaways is the importance of robust design and construction. Modern ships are built to stricter standards, with greater emphasis on hull strength, structural integrity, and fatigue resistance. Computer-aided design, CAD, and finite element analysis, FEA, allow engineers to simulate various stress scenarios and optimize designs for maximum strength and durability. Equally important are stringent inspection and maintenance regimes. Regular inspections, both in dry dock and at sea, help identify potential issues like corrosion, fatigue cracks, or structural damage before they escalate into serious problems. Furthermore, advancements in weather forecasting and routing systems allow ships to avoid severe weather conditions that could put excessive stress on the hull, reducing the risk of structural failures. The maritime industry is also exploring new technologies, such as structural health monitoring systems, which use sensors to continuously monitor the condition of a ship's hull, providing real-time data on stress levels, vibrations, and potential structural anomalies. These systems could provide early warnings of potential problems, allowing for timely intervention and preventing catastrophic failures. The image of a ship snapping in half serves as a stark reminder of the immense forces at play on the open ocean and the critical importance of sound engineering practices in maritime safety. While we have made significant strides in understanding the forces that ships contend with and designing more resilient vessels, the quest for safer seas is an ongoing journey. By embracing technological advancements, implementing stringent safety regulations, and fostering a culture of continuous improvement, we can minimize the risks inherent in maritime operations. The lessons learned from past disasters, as tragic as they may be, serve as stepping stones towards a future where ships can navigate the world's oceans with greater confidence and safety. As we venture further into the vast expanse of the sea, understanding the delicate balance between human ingenuity and nature's power will continue to be paramount in ensuring safe passage for the mariners and cargo entrusted to the waves.